So previously we have shown that the series 1 plus 1 over 2 to the power of p plus 1 over 3 to the power of p and so on converges when p is greater than 1 but diverges when p is less than or equal to 1. And so the natural case to try to evaluate first is the case p equals 2. Because that's the smallest positive integer value of p for which zeta of p converges. So we are going to try to evaluate the sum of the reciprocals of the squares of the natural numbers. But first of all, we see that it looks like the sum of zeta of 2k will be related for all positive values of k. And the reason we get this intuition is because if we square zeta of 2, for example, we get zeta of 4 plus another series whose exponents are even. So this is the series of the reciprocals of the products of the natural numbers taken two at a time, and we square them. So all the exponents here are even, and so this makes us feel that zeta of 2, zeta of 4, zeta of 6, and so on will all have related sums. So this is not the case for odd values of the exponent. For example, if we square zeta of 3, then we have a series where the exponents are even, but also another series where the exponents are still odd. So we are going to try to evaluate all of these zeta 2k values together. So perhaps there is a formula relating zeta of 2k in a recurrent fashion on the previous evaluations. So I mean that perhaps we can evaluate zeta of k using zeta of 2, zeta of 4 through zeta of 2k minus 2. So this is just a kind of intuition. And so, but this makes us think, so how do we evaluate the general term of a recurrent sequence? So we use generating functions. So let us quickly recap how generating functions can be used to find the general term of the Fibonacci sequence. So we recall this sequence is defined as f0 being 0 and f of 1 being 1, and then f of n equals f of n minus 1 plus f of n minus 2 when n is greater than or equal to 2. And using just this definition, we can produce the following generating function for the Fibonacci numbers. So this function x over 1 minus x squared, when developed as a power series, has the coefficient of x to the power of k being the kth Fibonacci number. And then we can decompose this into partial fractions, and we eventually find a closed form expression for the nth Fibonacci number in terms of the golden ratio 1 plus the square root of 5 over 2. So that was a brief recap on generating functions. So this suggests the idea of trying to find the generating function for zeta of 2 times x squared plus zeta of 4 times x to the power of 4 plus zeta of 6 times x to the power of 6, and so on. So naturally, we write out explicitly zeta of 2 as 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on. And similarly for zeta of 4 and zeta of 6 and zeta of 8. So the next obvious thing to do is to invert this double sum. So when we do this, we find that we get an infinite sum of infinite geometric series. And we can sum each of these geometric series because the first term equals the common ratio. And when we sum the individual infinite geometric series, we get the following infinite sum. So these are the first terms of each infinite geometric series, and these are also the common ratios. But when we look at this expression, we find that each of them can be written as the derivative of a logarithm times a factor of minus x over 2. So when we differentiate the log of 1 minus x squared over 1 squared and we multiply it by minus x over 2, we get this first term. And similarly, we just change 1 into 2 and 2 into 3 to get the other terms. But now this infinite sum of logarithms can be written as the logarithm of an infinite product by the nature of logarithms. And so we consider this infinite product here, and we find that this is a function with roots at x equals plus or minus 1, plus or minus 2, plus or minus 3, and so on. And this reminds us of the sine function, which has roots at x equals 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on. And now we are going to make a bold conjecture. Maybe sine of x equals x times 1 minus x squared over pi squared times 1 minus x squared over 2 pi all squared times 1 minus x squared over 3 pi all squared, and so on, because this expression on the right has the same roots as sine of x. But we must bear in mind that we have not rigorously proved this. We are just making a bold assumption. However, let us make the bold assumption and cavalierly move forward. When we do this, we find that sine of pi x over pi x equals this infinite product here. So that the generating which we wanted to find is equal to minus x over 2 times the derivative of log of sine of pi x over pi x. So this expression equals zeta of 2 times x squared plus zeta of 4 times x to the power of 4 plus zeta of 6 times x to the power of 6, and so on. And when we actually carry out the differentiation, which is easy, we find that this is equal to, after simplification, 1 minus pi x times the cotangent of pi x, all divided by 2. And this is very nice. So if we can now take this function and unfold it as a power series, then we can equate coefficients and we will have evaluated the zeta of 2k. Of course, we must bear in mind that throughout we have made this bold assumption here. So let us move forward. So for brevity, we denote this series here and hence this function here by f of x. Then let us try to find a more convenient expression for x, for pi x cut of pi x. So x times cut of x can be written as x times cosine of x over sine of x, which can be written in terms of the exponential function by making use of Euler's formula, which is e to the ix equals cosine of x plus I times the sine of x. So this formula unites trigonometric function and exponential functions, and when we do this, we can subsequently replace x by ix to find that ix times the cotangent of ix equals x times e to the power of x plus e to the power of minus x over e to the power of x minus e to the power of minus x. Then we can multiply both the numerator and the denominator by e to the power of x, and we can rewrite this as a sum of two terms as follows. So we can check that e to the power of 2x minus 1 plus 2 gives the numerator. And then we can distribute the x over each of these terms. So we have just got an expression for ix got ix in terms of the exponential function. Now let us go back to our function f of x. If we substitute x over pi for x, then we get 1 minus x got x over 2. Then we replace x by ix. And finally, we use the expression we have just got for ix times cut of ix to find that f of ix over pi can be expressed as follows in terms of the exponential function. So just to see where we've got so far, we found that this expression here, which is the negative of this expression, equals this infinite series, which is zeta of 2 times x squared over pi squared minus zeta of 4 times x to the power of 4 over pi to the power of 4, and so on. So this alternating series is given by this function here, which is written in terms of the exponential function. Now we are going to make yet another simplification. We replace x by x over 2. So then we obtain this equality, and then we simplify. So we multiply both sides by 2 and let only the term x over e to the power of x minus 1 on the left. So we get this infinite series here. And now, but we notice that we of course want to express this as a power series, because then when we are able to get the coefficients b0, b1, b2, b3, we can equate coefficients with this expression here and hence evaluate zeta of 2k. So as follows. So by equating coefficients in the two expressions, we find that b sub 2k equals minus 1 to the power of k minus 1 times 2 times zeta of 2k, all divided by 2 pi raised to the power of 2k. Or making zeta of 2k the subject of formula, we will have expressed zeta of 2k in terms of b sub 2k. And of course, now let us actually find the coefficients b0, b1, b2, b3, and so on. So to expand this as a power series, we make use of the Taylor series for e to the power of x, and then we equate this to b0 plus b1x plus b2x squared, and so on. But then when we cross multiply and equate coefficients on both sides, we find that 1 equals b0 plus b1x plus b2x squared. So there's a small typo here. This x cubed should have been x squared. So all this times 1 plus x over 2 factorial plus x squared over 3 factorial, and so on. And then we can expand the brackets and equate powers of x to find the recurrence relations, which will enable us to successively evaluate b0, b1, b2, and b3, and so on. So in this way, we can calculate any b sub k recurrently. And so, for example, we find that b0 equals 1, b1 equals minus a half, b2 equals 1 over 6 times 1 over 2 factorial, b3 is 0, b4 equals minus 1 over 30 times 1 over 4 factorial, and so on. And then, therefore, zeta of 2, using our expression we got previously for zeta of 2k in terms of b sub 2k, we find that zeta of 2 equals pi squared over 6, and zeta of 4 equals pi to the power of 4 over 90. And of course, we can in this way evaluate any of the zeta of 2k. So there's a couple of remarks to make here. So first of all, these evaluations using the recurrence laws for the b sub k's, suggests that instead of writing b sub 2k, we could write capital B sub 2k over 2k factorial, because the b sub 2k's are going to have a 1 over 2k factorial factor. So this just makes the denominators a bit more manageable. So then the expression for zeta of 2k in terms of b sub 2k are transformed into the following, and we can evaluate these capital B sub 2k's as b2 equals 1 over 6, b sub 4 equals minus 1 over 30, b6 equals 1 over 42, and so on. So we can carry these evaluations as far as we want. So that was the first remark. Another remark is that because of the recurrence we have found here, and the fact that b naught equals 1 and so is rational, therefore all these coefficients b sub 2k are rational. And so zeta of 2k divided by pi to the power of 2k is a rational number. So zeta of 2k is a rational number times pi raised to the power of 2k. So that's our second remark. A third remark is that we need to remember that we have made a very bold assumption when evaluating zeta of 2k, namely we have assumed the following factorization of sine of x. So what we want to do is we want to generalize the fundamental theorem of arithmetic. So we recall that if without loss of generality a naught is non-zero and a n is non-zero, then the polynomial on the left can be factored using its roots, so rho 1, rho 2 through rho n are the roots of this polynomial, and the fundamental theorem of algebra enables this factorization. So we would like to extend the fundamental theorem of algebra to functions other than polynomials. And so when we look at the Taylor series of sine of x, we would like to think of it as a kind of infinite degree polynomial and extend the fundamental theorem of algebra to it. However, there are very obvious problems to doing this generalization. First of all is the convergence of the product, which can be infinite if there are infinitely many roots. And secondly, as e to the power of x is non-zero for all values of x, clearly f of x and f of x times e to the power of x cannot have the same factorization, even though they have the same roots. So these are problems that are very difficult to deal with. However, it turns out that this factorization for sine is exceptionally correct. And later on we will try to prove this, but for now let us just notice that if we equate coefficients of x cubed in the Taylor series for sine and in this factorization, then we can immediately evaluate zeta of 2 to be pi squared over 6. So what we are going to have to do in the next videos is we are going to have to prove this result for sine of x at least, even if we cannot immediately have the full generalization of the fundamental theorem of algebra for all functions, for all suitably nice functions. But before even trying to do this, it would be better for us to try to obtain this evaluation of zeta of 2 in a rigorous way which does not involve making this assumption. So in the next video, this is what we are going to do. We will evaluate zeta of 2 in a different way, completely rigorously.